I'm sorry, what?
Little IOLA card thing. It's kind of fun.
Oh, you enjoy that?
Yeah.
I'm glad. Did everybody get a chance to play around with them this week? Yeah, they're kind of cool little devices. I kind of wish they would have added maybe just a few more things to them, but I suppose I should send them an email and tell them to do that on their next version of it. I think this is their second or third version. And I've met the guys who invented it, talked with them for a little bit, but I haven't emailed them in a while. Toyed around with the idea of building my own version because there are certain things that they put in that I wouldn't, and things that I would do very differently. So I bought a bunch of parts last year, and then all kinds of things started happening, and I didn't get a chance to ever build a prototype. So I have a bunch of parts to build a prototype. I just haven't done it.
You just use like a Raspberry Pi or something.
Yeah. But my intention was to make it like in this car, it uses a device attached to the wheel to determine how far it's rolled. So the wheels have to be rolling for it to work as far as the movement sensor, linear movement sensor. I think that I would use instead of that, or maybe in addition to that, a ultrasonic sensor that would sense distances to an object, so that you could roll it, towards a wall, and it could tell how far away it was from the wall or something. I found that those devices have, I think, more uses, but that's just me, I guess.
I do have a question for you. Is there late passes on how does it work?
The late passes work like if you're getting to the end of a homework assignment and it's about to be due and you just want to finish it up, you can just click on it and it'll just grant you an automatic late pass. But if you need to get an extension, just send me an email and I'll just extend it. That's how
I just see like they said use late pass and you can click on it.
Yeah, and you can. And using the late pass, the track's like 5% or something per hour, or 10%. I don't know. It takes some points off. If I extend it, it doesn't. So it's just, but it's up to you if you decide you want to use it or not. Okay, let's see what we're going to get done today here. Can I just close that, I guess? All right. We are on chapter 4 today, right? This is the wrong class. Two, three, 4. Yep. We answered questions on chapter 3. I haven't checked the grades, but if you had any struggles from chapter 3 that we didn't get to on last Wednesday, just send me an email. We can catch you up. The lab that we did last week was lab 2, I think, something like that. Maybe lab 2 and lab 3. What did we do? Just lab 1? Oh, so we should do lab 2 and lab 3 probably. Let's take a look at those labs really quick and see which ones are good ones to do.
You did go over lab 2 if you want to go ahead.
Oh yeah, definitely get into lab 2 for sure. We'll check lab 3 too and see what that one's at, what that one's like here. I've had 3 different people, 4 different people turn in 4 different lab reports, completely different from each other, and that's totally fine. Don't have any problem with that. I just want to see that you've learned something, that you've connected it somehow to the homework and stuff we're doing in class, that you've explored something, and if you've had any questions, that you've asked those questions. So, and I just have to warn you that I'm terrible at going actually in and entering grades in for the labs. So if you don't hear anything, that's probably good news. It probably means I've looked at your lab and said, oh, that looks great. And then I've just gone on and done something else. and you'll probably get, full credit or almost complete full credit for that lab. It won't hurt your grade at all. It'll probably just help your grade. So it's nothing to really worry about if you don't see those grades popping up in the homework or in the on My Open Math. The best way to estimate how you're doing in the class is to just kind of look at your average homework and your average exam and take the average of those two. And that's usually the best way to see. I can actually set it up so that it gives you a real estimate grade or something, but it doesn't do any better than just looking at it, honestly. It's about the same. Come on, where's my... That's not the one I'm looking for. Yeah, I have it over here actually. Oh no, I don't. Oh, did I put it in my Open Math? That was smart of me. I just didn't think to go click on it. There we go. That's the one. Thank you. Thank you for telling me what I've done already, because I'll never remember what I do anytime. All right, so lab two is the ramp one. We did talk about that one a little bit. So going up and down the ramp, of course, that can be considered one-dimensional or two-dimensional kinematics, really. So that's great. Lab three, I think lab three, you put a mass on it with a string or something. Let's take a look. No, it's still on a ramp kind of, but this time you're using the force device as well. So the force device is the thing on the end. You can plug a little eye bolt into it, or I think you can put a little bumper on it, a little like disc on it or something like that. So they're having you do different things with forces here. And that one's not too difficult, of course. Well, already wake up here. This one is this is just another one using, this is looking at acceleration with the accelerometer. So you can actually just keep doing these labs as quickly as you want to. Don't take too long on them. They're not terribly long activities. We will do most of them. So, and then we'll do some extra ones as well. Here's the one with the string and the mass on it. I don't think I included a mass in the kit at all, but you can just use anything, tie like a small ball onto it or something. I don't know. Doesn't need to be a very big mass, talking like a couple of quarters would do, or, tape a quarter to a string or something like that. And that would probably do it just fine. Doesn't take much. That was lab 5. I just did lab 5. Lab 6. At some point here, they get into some other thing that's, so here they get into rotation. So we want to go all the way through lab 5 here while we're doing this stuff that we're doing. So you can go ahead and just try to do a couple of labs a week here from now on, now that you know how to work the thing, and keep going while we're working on the different chapters. We'll get to rotation right about chapter, I don't remember when we get into there. Let's take a look here. Actually, chapter 6. So we've got this week and next week, and then we'll be in rotational stuff for a little bit, not much. We really get into it at chapter 10, I guess. Well, yeah, chapter 9 and 10, we get into rotation. So got a couple of weeks where we can do some other things, and I'll give you a different, I'll give you another lab for working for energy and a lab for momentum and collisions besides the ones that we looked at. But by the time we get done with chapter 10, we want to be done all the way through 7, I guess, on that list of labs. Is it 7? Yeah. Or 6. Must have been 6. Yeah, we want to get all the way through lab 6. And then lab 7, I don't know what that is. I don't remember now. Yeah, so lab 7 is going to come on later. We'll skip from lab 6. We'll do a couple of activities that are outside of this this group, and we'll still be using the tools that you've got. We'll still be using the IO lab and things that you've got at home, other things like that. And then we'll come back to lab 7 and take a look. I don't remember what lab 8 is either. I think it must be. Yeah, it's another pendulum thing. That's another oscillator thing. So we'll do the lab 7 and lab 8 near the end of this semester, end of the summer. So anyway, moving on. We are now in chapter 4, moving on to chapter 4, dynamics, which is the beginning of what Newton really did for physics. A great picture of dolphins in captivity. Just makes you smile, I guess. When we were first married, we had I guess we weren't first married, 5 years into our marriage or something like this. We took our three oldest kids, who were quite young at the time, and we took them to California, where we grew up. And we were walking on the beach near Santa Cruz in California, which is kind of like right in the middle of California. It's just south of San Francisco. And me and my wife had grown up there all of our lives. You know, we'd been to the beach so many times, and we'd never experienced this before. But we're walking across the beach, and all of a sudden our daughter, who's maybe 5 years old, 6 years old, points and she says, "Look, dolphins." And there's this pod of dolphins going across the bay, and we're like, "Whoa." I mean, you never just see that from the shore. It's pretty rare, especially near California coast. It's just not that common. There's too many people, too much noise, too much pollution, all that crap. It was really cool. Have our daughter point that out on her very first trip to the ocean. So anyway, all right, here's the book written by Newton, the first physics textbook, Philosophia Naturalis Principia Mathematica. Of course, back then everything had to be written in Latin so that you looked smart, I guess. I don't know. They did all their numbers in Roman. How do you do math with Roman numerals? Right? MX1111 plus MXV11V1V, whatever, equals what? I have no idea. It's a stupid number system. No wonder the Romans got conquered. Anyway, you ever thought about singing 99 bottles of beer on the wall using Roman numerals? Oh, man, that would suck. Oh, anyway. Okay, so there are a lot of people, though, at the time when Newton came along that had done a lot of work before him. Galileo was a huge contributor to physics. He observed so many things moving through the heavens, and and it's commonly thought that Newton actually, the whole story with the apple falling on his head, who cares if it happened or not? That actually had nothing to do with what he was studying. He wasn't studying how things fell on Earth. That had already been well established, how things fell in the gravitational field on the Earth. He didn't do anything really with that. His study was mostly based on what was going on out in space, planets attracting each other, stars attracting planets. He was mostly dealing with our solar system and moons going around, like the moons going around Jupiter. He was studying the motion of planets mostly, and that's where he got a lot of his information, and that's where a lot of his theories were formed, and a lot of the laws that he was able to kind of eke out of all this data. that's where it came from, is those kinds of observations, not necessarily the apple falling out of a tree kind of stuff. It all applies, of course, it's all relevant to everything, but this goes far beyond just the simple mundane things of everyday life. And so what are Newton's laws? To really understand Newton's laws, we have to understand another concept first, and that is, what is a force? So the most common definition for a force is this idea of push or a pull, right? And that's a great definition. It's not necessarily a perfect definition, but it's a great definition, especially for starting off. When something is pushed or pulled, then it's experiencing a force. Newton defined it a little bit better. We'll get to that in a minute. And even later in the 20th century, it's been defined even better by Einstein and others. Planck and some great physicists of the 20th century were able to truly define force in a much more general and fundamental fashion. We'll learn about that later too. But the fact is that a push or a pull is a great definition for now, for sure. And if you're feeling a push or a pull, you're very likely feeling some kind of a force from something. We often think of a push or a pull as requiring contact, like in this case here, where we have these ice skaters, and this ice skater is going to push from this direction towards the right. This skater is going to push from this direction towards the upward part of the screen, I guess. And the whole idea that forces might have some direction suggests that they're probably vectors, of course, and they are. They should be treated like vectors with a magnitude, which would be the amount of force, or the amount of push or pull, and a direction, which tells you which direction that push or pull is pointing. And of course, that doesn't have to be constant. You can increase or decrease the amount of force. You can change the direction of the force. We're going to try not to do that as much as possible because it makes the math hard. But you can add them together just like you can add any forces to vectors together. If you have a force in this direction and a force in this direction, it's kind of like two components of another force that goes off in this direction, right? And likewise, you can take a total force in this direction and break it into vectors in the x and y directions by using the component mathematics we learned in the past couple of chapters. So all of this is very relevant to what we've been doing so far. It's very connected and not going to be much new to do with that. When we do draw a picture like this, and we will draw a lot of them, you should draw a picture like this for every problem that you do. It doesn't have to be ice skaters. It should be relevant to the problem you're doing. But we often draw a more simplified version of the picture that we call a free body diagram, which shows the object that's being forced, or the object where the forces are acting on, is represented as a single point if all the forces are acting at a single point, or as a simple shape if the forces are acting at different points on the object, which will come in later in the class. And we call this a free body diagram because it's as if the body, it's as if we've freed all of the problem from all of the weird stuff that could be going on and created this very simple problem that only has these forces acting on it. And so it's a free body in that everything we've drawn is there. There's nothing hidden. There's nothing kind of implied. This is it. This is the only thing happening to this body. There's a force 2 acting upward. There's a force 1 acting to the right. If this skater already had some particular velocity before they started pushing around, then you might indicate that somewhere in the diagram or the drawing. And the reason that they use ice skaters, of course, is because when we stand on the ground, there's something that prevents us from being pushed around. What is it? Friction, right? Between our feet and the ground. And we notice that friction a lot when it's gone, right? We notice the lack of friction when it's wintertime and we step out and there's no friction, and whoop, right? So ice skaters don't have very much friction between their skates and the ice. And so we can we can say with some degree of confidence that these two forces are the dominant forces, and any other forces are either not there or very negligible. And so a free body diagram is going to illustrate those forces. It's also going to be only external forces that we're going to draw on here. For example, if the skater is standing there holding her wrists and pulling on her wrists back and forth, we're not going to include that force because that's internal. It's her acting on herself. And sometimes it can get a little bit confusing to determine which forces are internal and external. But you just have to think, well, what is not part of the object of interest that is acting on that part of that object of interest, right? So external forces are put on those diagrams. So here's a little bit less obvious one. We have a spring with a handle on it, and it's connected to a wall. This is their version of a wall, I guess. And we're going to pull on this spring. We're going to pull it this way to the right by exerting a force this way. Get my drawing tools out here. So our hand is actually pulling this way with a pulling force. And if you've ever done this before, pulled on a rubber band or a spring or some kind, you know that it actually pulls back, right? If you let go, it takes off because there's a force backwards the other way. And that's what's called a restoring force. And many objects do exert a restoring force if you apply a force to them. It's very common in nature. So that's something we'll deal with. The interesting thing about many restoring forces is they often depend on how much force you exert. If you stretch the spring more, it will actually pull back more, right? You know that stretching a spring a little bit takes very little force to stretch it, and it doesn't pull back on you much. But if you try to stretch it more and more and more, it gets harder and harder and harder to the point you get to a point where you really just can't stretch it anymore with the strength that you have. So restoring forces are interesting forces in physics in general. One of the more common restoring forces that we don't really think of as a restoring force is the restoring force that is gravity that keeps us on the planet's surface, right? We're on the planet's surface and gravity is holding us on that surface. And if we jump up above the surface, what happens to us? Gravity restores us back to the surface. Gravity pulls us back down to the surface. And so I've always thought, well, if you could dig a hole all the way through the earth, could you jump down into it? And then just get accelerated faster and faster and faster. And then when you get to the center of the earth, you go through and then it'd slow you down. And then you'd come popping out and you'd say hi to Australia and then you'd go back in. And you just go back and forth like you're on a spring in the middle of the earth. Theoretically that would happen. Since we've never dug more than a very, very tiny portion of a 1% into the Earth's crust, hard to imagine how we could do it. But. So this brings us to the laws of motion, of Newton's laws of motion. After Newton spent many, many years observing what was going on in the universe around him by observing all the experiments done by Galileo and Kepler and so many others, he observed that there were three things that always happened. And he created his three laws of motion from those three ideas. The first thing that he noticed is that there is this property of things with mass that causes them to not want to change what they're doing, right? So if something is moving along through space, it wants to keep moving along through space. And unless you force it to do something else, it's going to keep doing that, whatever it was doing. And we call this law the law of inertia. Inertia literally comes from the word inert. The word inert means to not change or to be not affected or not affecting things. So inertia means unchanging or not changing, right? Or not wanting to change. And inertia is a direct result of the mass of an object. The more mass an object has, the more inertia it has. So if you want to measure how much inertia something has, you measure how much mass it has. Something that is much more massive, it's much more difficult to change what it's doing. Have you ever been pushing a big truck or something because it's not starting, and then tried to stop it from rolling? It's not easy. In fact, getting it going is not easy either, right? Because it's got so much mass to get those things going. You know, it's really difficult to stop them. It's really difficult. So not a good idea to be in the way when they're trying to stop. Trains the same way, right? There's plenty of, you want to see horrifically funny videos. Watch boats coming into dock when they're being piloted by somebody not knowing what they're doing or not being piloted at all. And a boat comes in and they're not slowing down, and you realize there's 40 tons of boat coming in, and it's not coming that fast, but it's not going to stop either. So it just comes in and just plows through the dock, and people go running and flying off the dock and goes up the shore, and it can cause all kinds of damage, and unfortunately it can cause all kinds of pain and death as well. But it's happened more than once in the world where somebody wasn't paying attention when they were coming into dock, because you pretty much have to be stopped when you hit the dock, because there's so much, you have so much inertia, it'll just keep going. Nothing will stop it unless it's like going up on the shore. The shore is the only thing that has enough mass to stop a boat, really. So the law of inertia, it's often stated as let's see, what are some of the things that people say about the law of inertia? An object in motion will stay in motion. That's a common one, right? And that's not a very complete description of this, because we already know that motion takes on more forms than just one. We've already talked about a couple kinds of motion that are not necessarily the same exactly. So what kind of motion are we talking about? Well, truthfully, the best way to state this is that an object that is at rest will tend to stay at rest unless something forces it to accelerate in some way, forces it to change that. An object that is in motion in a straight line, constant velocity, so constant speed, constant direction, will tend to stay in that motion. There are some other variations on that, because you can also have rotational motion. Rotational motion, such as the rotation of the Earth, will continue to rotate because it has a moment of inertia or rotational inertia. And that rotational inertia is a real thing as well, but it has something to do, it's a little bit different, not just mass. That's the same reason that the planets continue to go around and around the sun. Well, it's a similar reason, because the entire solar system was just a huge mass of rotating junk, billions of years ago, and eventually kind of coalesced into planets or whatever. So it's interesting because this idea of things continuing to do what they're already doing is very, very, it's obvious looking at the universe, even though we can't really look back and see how was the universe created. Regardless of how you feel about the universe being created, it doesn't matter if you feel like it's it was an organized thing by some intelligence, or if it was just a random accident, some cosmic roll of the dice, or some goofy thing, or somewhere in between. It doesn't matter. It doesn't matter what you think of it. These things are evident. You look in the universe and you say, wow, why is everything going the same direction in our solar system? Something had to be all happening at the same time. And this is the best explanation that has ever been come up with. And he came up with it 400 years ago. And that's pretty amazing. So, and especially at a time when, it was really not cool to come up with ideas that were anything different than whatever else people were thinking at the time. So anyway, that's Newton's first law, is this idea of inertia, and it is directly tied to mass. Newton's second law is the thing that causes these things to change what they're doing. So what causes something to change what it was already doing or not doing or whatever, right? What causes that inertia? What changes the the object has that inertia? Well, it's a force. So Newton's second law of motion says that a force causes an acceleration for a mass, okay? And as Newton was studying this, and other people were studying, Galileo studied this as well, they discovered that there was a direct relationship between force and acceleration. So if you increase the force by double on a particular mass, you will increase the acceleration by double. But they also discovered that if you change the mass in the experiment, so if you keep the same force and you double the mass, the acceleration goes down by half. So there's an inverse relationship with mass, right? And the law comes out really quite cleanly as force equals mass times acceleration. They write it here as acceleration. No, here, sorry. Here they write it as acceleration equals force over mass, but it's usually quoted as force equals mass times acceleration. Now notice that it's a vector equation. These are boldface, and that's what we use for vectors in this book. So force is a vector, acceleration is a vector. Mass is not a vector. Mass is just a number. It just tells you how much mass there is. There's no direction to it. And so this tells us something else as well. This tells us that the force is also going to be in the same direction as the acceleration, because those are the only vectors in the equation. So they have to be pointing in the same direction if there's an equal sign between them. Plain and simple, right? There's also this little thing that says net force. The net force means the total force. So you can't just, look at one force on an object and then look at the acceleration of the object and say that force is equal to the mass times that acceleration. You have to make sure that you have added together all of the forces on the object, and then all of those forces combined will equal the mass of the object times the acceleration of the object. You have to add them all together. And so that becomes quite important. Again, you need to get used to drawing pictures and free body diagrams, but you also need to define your system. It's important to define what is the object that you're interested in. Here's one situation where we have a system is our child and the wagon he's sitting in. So what are the forces on the child and the wagon he's sitting in? We've got all these forces labeled. Which forces are acting on the wagon and the child from external to the wagon and child? What are the external forces? I'm sorry? I can't hear you, sorry.
The two people behind.
Oh, so these forces, force 1 and force 2? Yeah.
I can't see, is that an F in the front?
Yeah, F1, F2 right here. These two forces are acting on the child and the wagon. So they're both acting on the object of interest. Any other forces acting on the child and the wagon?
One right over there.
Right, this one right here, they're labeling as friction force, right? So that's friction. And then what is this one here? That's the weight force. That's the weight of the child plus the wagon. So they're just calling that one force. Technically, that force pushes on the ground at the points of the wheels, but we're not talking about where it pushes on the ground. We're talking about where gravity pulls on the wagon. Gravity pulls on the wagon as if it's acting on the center of mass of the wagon and the child, which is kind of where the center of all the stuff is, right? So they put it right in here somewhere. And then here they have this force. This is called a normal force. And technically, this one actually should be acting on each individual wheel. What is this force, do you think, that's pushing up on the wagon?
Is that just the ground?
Yeah, the ground actually pushes back because the wagon is being pulled down by gravity, but the ground pushes up on the wheels. If it didn't, what would happen to the wagon? It would go flying down towards the center of the earth, right? So anytime you're standing on the surface of the earth is pushing up on you. There's always a force. And we call that the normal force. We don't call it the normal force because it's a regular guy kind of force. We call it the normal force because mathematically normal means perpendicular. So when any two surfaces come in contact with each other, whether it's your feet on the ground or a wheel on the ground or your hand as on the wall as you're resting against the wall or whatever, your butt on your chair, doesn't matter. Any two surfaces come in contact with each other, there is a force that prevents them from moving through each other, which is usually the case with solids. And that force is perpendicular to the contact between the two things, whatever they are, right? So so that's why we call it the normal force. If you're a skier on a hill, which we'll see an example of soon, if you're a skier on a hill, that normal force is perpendicular to the hill, right? And so that force that's perpendicular to the hill is no longer perpendicular to your weight, which is up and down. And that's why you can slide down the hill, because some of your weight is actually pulling you down the hill and some of it is keeping you on the hill, right? You get to a point where that hill is no longer a hill, but it's like a cliff, then your skis go flying off because there's no normal force anymore, right? And you go flying, which is kind of fun to watch for skiers, or for people watching skiers, I guess. Here's a different system where the system, this one only has one person pushing, but still pushing on the child. And since the child and the wagon are the full system, then this one has just one force pushing on the system forward. But what if we chose just the child in this system as our system of interest? What if we said we don't care what's happening to the wagon, we just want to know what's happening to the child? Well, then this force 2 from the child in the back there in the purple dress would be the only force pushing on the child alone. And there wouldn't be any friction force between the wheels and the ground in that problem. There would be a friction force between the child and the wagon, because the wagon is pushing the child forward using frictional force. And there might be a contact force between the back of the wagon and the child. If the child's leaning against the back of the wagon, there might be a normal force back there. There's definitely a normal force between the child's butt and the bottom of the wagon, where they're sitting on the wagon and their weight is pulling them down, so the wagon is pushing the child up, right? And because the child is external to the wagon, or the child is the system of interest and the wagon is external to that, it looks like the child is pulling back on this handle, doesn't it? And if the child's pulling back on this handle, have you ever done that in a wagon? Is there a restoring force? Does the handle want to pull back that way? It kind of does. It kind of has that springy pullback kind of thing going on. So there would be maybe a slight springy pullback force from the handle on the wagon. And we'll learn more about that pullback force here in a bit too. So there's a lot of things to think about, and you have to make sure that you account for forces that are all there. Sometimes you ignore some forces because they're negligible. They just aren't going to affect much. They're very tiny. And in this class, usually we think of it as, the friction is negligible. We're just going to say there's no friction in this problem. That's not always true, but it sometimes just makes the math a lot easier. And that's why we do a lot of things on snow and ice, because in those cases, the friction is pretty negligible. All right, anyway. So here's a great example of Newton's second law. You have a basketball and you push it forward with some force. Force is measured in the units we call newtons, which are kilograms meters per second squared. So that's the unit for force. So if you push on a ball with 10 newtons, you're giving it 10 kilogram meters per second squared of force, okay? Just so you know, 10 newtons is not a lot of force. My weight, for example, is around 1,000 newtons. That's why we don't use newtons to measure our weight, because it would make everybody feel terrible about their weight, right? Of course, my weight's not even great in pounds, but newtons are a much, much smaller measure of force than pounds are. So 10 pounds is about, our 10 newtons is only a couple of pounds. So if you give a couple of pounds of force to a basketball, you can get it moving a little bit. Give that same force to an SUV, doesn't do much, right? Much smaller acceleration because the much bigger mass. Incidentally, if there's no friction between the wheels in the bearings of the wheels, and if there are no other forces on this car, because it's a perfectly built car and it rolls perfectly without any friction, and you put that car on the moon, you would get the same reaction from the car with that same amount of force pushing it sideways. Why is that? Well, because gravity downward doesn't affect forces sideways. Remember, there's this independence of motion thing when you have 90 degrees to your motion. If you have a downward motion, a sideways motion, those are 90 degrees to each other. They don't affect each other. So gravity has nothing to do with rolling a car. Lifting a car, it has something to do with it. So, you know, you get around an SUV with a bunch of people and you lift it, it's going to take a lot of people, 20 people probably, with good handholds on an SUV. If it's a Volkswagen, it takes one Wilt Chamberlain. You ever hear that story? Do you guys know who Wilt Chamberlain is? Oh man, dealing with children. Goodness. Just kidding. Wilt Chamberlain is a little bit before my time too, but because I am a Warriors fan and I'm also a volleyball fan, I love Wilt Chamberlain. Wilt Chamberlain was a professional basketball player back in the 60s and the 70s. And I can't remember if he retired before the 80s or if he played a couple of years into the 80s. I think he may have played a couple of years in the 80s, but I don't think so. I don't remember. But he was 7'1", 7'2", or something like this. He was probably the greatest athlete who ever played basketball and maybe one of the greatest athletes of all time. He set several records in track and field as a 7-foot person. He set a record in the high jump without ever practicing it. He never actually did it. And he set a record in the high jump. And this is before they did the Fosbury flop going over backwards. He just scissor kicked over it and rolled over it. But he was incredibly strong. He actually did a movie with Arnold Schwarzenegger back when Arnold Schwarzenegger was an actual like strongman bodybuilder. And he used to work out with Arnold Schwarzenegger. And Arnold Schwarzenegger said he could outlift, Wilt Chamberlain can outlift any professional weightlifter in the gym without any trouble. But Wilt Chamberlain once picked up a Volkswagen with one hand. He just leaned over, grabbed it by the bumper, and lifted it up off its front two wheels. That's like 800 pounds with one hand. That's insane. It's also been said that he actually bench pressed over 1,000 pounds. But very strong person, an incredible jumper. When he was playing against the, I think it was the Lakers actually, and somebody taunted him in the game saying because they were beating the Warriors, and this was back when the Warriors were in Philadelphia. And Wilt Chamberlain said there will not be another basket made on this end of the court, on his end of the court. And for the rest of the game, the second half of the game, he blocked every single shot made on that end of the court. It's incredible. He was just an incredible athlete, an incredible, like, strong person for some crazy reason.
It sounds fake.
Oh, it totally sounds fake. He still owns the scoring record in the NBA, and nobody's come close. The closest to ever come to it was Kobe Bryant. Kobe Bryant scored 81 points and didn't come close because Wilt Chamberlain scored 100 points in a single game. I mean, there are two people that have scored over 80 points, him and Kobe. And Kobe didn't even come close. And he also, I mean, get this. He averaged 41.5 minutes per game. No, 49.5 minutes, or maybe it was 50.5. That's more minutes than are in an NBA game. That's how many minutes he averaged for his career. So he played every minute of every game plus some overtime. He never rested. The guy was a beast. It was totally crazy. Before they did any of this, you know, supplements and personal trainers or anything else, he was doing this kind of stuff. He was an amazing basketball player. But anyway, all to do with force, he lifted up a car by himself. So the whole reason behind that story, which I never got to, I have a tendency to, you may have noticed, to rattle on and then forget what I was talking about. But the point of that is that if you lifted this car on Earth, it'd take 20 people. But if you took it to the moon, you could do it with maybe 4 people or so, maybe less, because you're lifting the forces are now in the same direction. You have to then gravity then is not pulling as hard. But if you're just rolling the car on the moon, it doesn't make any difference. Still, the same amount of force will give it the same amount of acceleration because of that independence of motion, right? So it's important to kind of realize and remember things like that as we go through and learn about forces. All right, so gravitational force, of course, is what we call weight. The weight of an object is the gravitational force. I actually think this is a misnomer. Weight is actually the normal force that pushes back on us, I think. because that's what we feel. When we feel weightless, it's because we don't feel the earth under our feet, right? When we lose weight in the elevator, you ever done that before? You go in the elevator and you're like, "Ooh, I'm feeling light," right? It's because the elevator dropped out from under your feet and it's not pushing on your feet as hard. And then you get to the bottom, you gain weight and you feel really heavy at the bottom, and then it stops and you're fine again, right? So it's like the quickest way to lose weight is go jump in the elevator. You can take one of my scales. I got a fuzzy green scale from circa 1975 here. And you can take it and put it in the elevator and go down and watch yourself lose weight, and then watch yourself gain weight, and then watch yourself go back to normal weight. And in between, when it's going at a constant velocity, what's happening to the scale? Like you start off by accelerating downward, and then you go to constant velocity for a second or two. And then you slow down at the bottom and you decelerate or accelerate in the opposite direction. During those accelerations is when the scale changes. You lose weight here, you lose normal force here, and then you get more normal force when it slows down at the bottom. But in between, what's happening? If you're just moving along at a constant speed in a constant direction, nothing happens. It's kind of like tied to that whole inertia thing. You don't even notice when you're moving along at a constant speed in a constant direction. You don't even really notice it, right? You're doing it. Drive along in your car, middle of the night, tired, straight line driving, doing it for hours, and all of a sudden you realize I'm still moving, and I don't even think I'm moving because you just saw a car go by or something, right? You're like, oh, I'm moving still, because you just stop feeling when you're in an airplane. You don't feel it anymore. You're just sitting there in an airplane, you're not feeling any movement. You just go until they have some kind of crazy, turbulence. So in the middle, you're back to your normal weight on that thing. So how do they give you that weightless feeling? Well, they take you up in an airplane like this. Put you in an airplane. Here's the airplane. They call it the vomit comet. That's what NASA calls it. A lot of people throw up in it. And they take you in this path that goes up like this, and then it tips over and goes back down like this. And for this region in here, there's a region in here where the weight from gravity pulling you down is there's a region in there where you're moving. You start by moving upward, so your body is moving this way, and then as the plane tips over, you're still going up a little bit, but the plane's now starting to go down a little bit. So in other words, gravity is not accelerating you fast enough to catch up at the bottom of the plane. So there's no normal force between you and the plane. And that's what we call weightless, right? And that's why I say the normal force is actually our weight. What we feel is the ground pushing on us. We don't feel gravity pulling on us. We feel the ground pushing up on us. That's what we feel, right? So that's what they do to make you weightless, is they take you up in this, they get you going upward in the plane, then you take off your seatbelts right here, and then they start the plane tipping over. And as it tips over, you keep going up, and the plane starts to go down or starts to flatten out. And so you're flying along. If you were looking inside the plane, this is what it would look like. You start here in your seat, and you're going up this way, and you keep going up this way while the plane starts going this way. And so there's this gap between where you're going and where the plane is going. It's your inertia, Newton's first law, that allows you to keep going, and the plane falls beneath you or turns beneath you so that you don't have anything beneath your feet. You ever seen anybody in the vomit comet? You ever seen people do the whole weightless plane thing?
It looks like it.
What's that?
It's a weird looking plane.
They can use pretty much any plane for it. I've done it in a Cessna.
Really.
Yeah. The guy out in Cozad took me and my son flying because my son was doing his flight test. He actually took his first flight test before he got his driver's license, which was kind of cool. But he didn't take any more because they're super expensive. I paid for his first one, but he has to pay for the rest. But anyway, we did it in that plane, and it's just that all it is just about turning the plane down, going up, and then turning down fast enough that it happens. It won't happen for very long, but there's this great music video about that actually. These guys do this music video on this plane. These guys are super funny. They're nerdy too. I like nerdy musicians. So this is just in a kind of a small private plane. It gets really good later though. You gotta watch the end here. Wouldn't that be so cool? And then the best part is when they start popping paint balloons. Anyway, wouldn't that be a fun job? Going to zero gravity. And I mean, but all that's happening really is the plane is just going one way and they're going the other way so that they don't hit each other. At some point in the flight, they could actually sit on the floor upside down and feel gravity on the ceiling rather, and feel gravity on the ceiling instead of the floor. There's one point in the flight where you feel that way. And then another part of the flight where you feel extra gravity as you turn back up to try to go through, because they go up and down several times usually when you're going through one of these flights. And sometimes called the vomit comet because sometimes it's not paint flying around in there. So gotta love it. Yeah. But kind of funny too. All right. So I think we've already talked about the difference between mass and weight, but weight we just defined as this force that we feel because we're being pulled towards the earth and the earth is pushing on us, right? It's that kind of interaction between object and earth, or object and surface of some kind. That's the weight that we feel. And mass is literally the amount of stuff. Mass is the amount of matter that causes the inertia thing to happen. And it seems like not that big a difference, or not that important, or whatever. And it seems a little subtle, but it's actually extremely important when you get into things like chemistry, for example. It's extremely important there. Extremely important in many things, actually. But let's go into a couple of calculations, just some simple things here. We have a person pushing a lawnmower here, and they tell us the net force. So they've already added all the forces together for us, and they told us that the net force is forward. We know that he's not pushing forward on a lawnmower, because anybody who's mown a lawn knows that you don't actually push forward, you actually push downward a little bit. And that's because the handle is pointing downward. You can't push forward on the handle without it pushing downward on it, because the handle will rotate forward and then it will push the thing downward anyway. It's just the natural thing. Whenever you're applying a force through an object, it has to go through the object. So the force from the person is actually pushing downward here, but there are some other forces involved that are created and that happen that create a total net force, which is forward. For example, there's a normal force upward in here, and there's some other things going on. But they've told us the net force, and that's fine because that's all we need. If we know that the lawnmower's mass is 24 kilograms, then calculating acceleration is just a matter of plugging numbers in. We're going to calculate an acceleration of 2.1 meters per second. And why can we do this without dealing with vectors? Because we've already said we need to deal with vectors. Well, because this is in one dimension. The net force is forward, and we know the acceleration is going to be either forward or backward. If it starts off with zero velocity, it'll be forward. If it starts off with velocity already going forward, the accelerate, it'll be going forward, and the final velocity will be whatever it'll be if it starts off going backwards, whatever. But we know that it's going to go back. It's not going to accelerate down. You're not going to push the lawnmower through the surface of the earth, and you're not going to lift it up from this position either, right? So it just makes sense that it's either going to be forward or backward. So this all becomes one dimensional. And in one dimension, you can just treat this like an equation without, vectors. We just need to remember that direction matters. So the acceleration is 2.1 meters per second squared. That doesn't tell us the velocity. It doesn't tell us, it just tells us what the acceleration will be. And that's fine. Here's another example where we have a rocket sled, where we have 4 rockets on the back of the sled that are providing thrust. And you have a friction on the front of the sled, which is going to slow down the sled a little bit. And we have a normal force and a weight force. And notice that the normal force and the weight force are equal and opposite. And that will almost always be true if you're on a horizontal surface, that your normal force and your weight force will be equal and opposite, as long as you don't have any other forces in that direction. If you had something else pushing down on the sled from above, so in reality, for example, if you're doing a race car, let's see.
Will those thrusters count if the surface wasn't perfectly?
So the thrusters wouldn't count unless they were pointing upward, so they were pushing it downward. But if you look at a Formula One car, for example, Formula One cars are very famous for having these surfaces on them. My favorite one is probably the Mercedes one. Here it is. But Mercedes has all these different surfaces. You can't really see them from there. I want to see a front view of it. A more frontal view anyway. Here's a good front view of one of these things. So you have this back spoiler here, and you can see there's these veins in this. And on the front, there's 1, 2, 3, 4 wings, and then a bunch of them over here as well. And there's this weird thing here. And you can even see that there's kind of some things out over here. And right up here, there's even things. You're like, what is all this stuff on here sticking up? And nothing on this car is superfluous. Nothing. Everything on this car has something to do with making it go faster. Okay, that's what Formula One racing is about. It's all about going faster. Here you can see a better view of some of these things. Each one of these things has something to do with it going faster. And one of the things that all these wings and things on it do is they actually provide downward force on the car, because air that gets underneath the car has to go the same speed or faster than air on top of the car in order to keep the car on the ground. But air does not go under these cars very easily. So the air under the car usually ends up going slower, which makes the car lift off the ground like a wing, like a plane. And if it lifts off the ground going 200 miles an hour, you're in bad shape. And so what they do is they actually add extra force to the top of the car by putting all these wings on that are kind of like upside down wings that force the car down. They keep the car down on the ground. That makes less air going under the car and more force pushing the car down. So it just makes all kinds of things work better for these things. It's on all kinds of racing cars, and even just cars on the road are designed to keep the air flowing in the right ways and to keep force down on the car when it's going fast, keep the wheels on the ground, that kind of thing. It's all about, safety and going faster and stuff like that. So unless you have something like that pushing down or pulling up or whatever else, then these are the only forces really acting on this thing. Since we have 4 rocket thrusters, we have 4 thrust vectors off the front and one friction vector. So when we add all these forces together in the vertical direction, the forces are going to cancel out because there's no other forces in those directions. That means we know that the weight and the normal force have to be equal and opposite because we know there's no acceleration in that direction. So we can turn this into a one-dimensional problem again and just add them just like numbers. So net force equals mass times acceleration. We know that the net force is 4 thrust forces forward, those are positive, minus 1 friction force backward, which is negative. And if that has to equal mass times acceleration, then this equation is true. And if we're solving for the thrust, then we solve for the thrust. We are told the acceleration, we're told the friction, and we can say that 4 times the thrust equals mass times acceleration plus friction. And we can solve for the thrust. So that's what they do. They solve for the thrust, 2.6 times 10 to the 4 newtons, and that's a pretty good amount of thrust for a rocket engine. Now, Newton's third law. So Newton's first law, inertia. More mass, more inertia. Right? Newton's second law, force equals mass times acceleration. If something is accelerating, there's a force pushing in that direction. Plain and simple. There's a net force pushing in that direction, in the same direction as the acceleration, if something is accelerating. Remember that that has nothing to do with velocity. Acceleration and velocity are not necessarily really related to each other unless you know something about the initial or final velocity and the time or something like that. You have to know something else about the motion to really get anything about the velocity out of acceleration. So if you only know the acceleration, all you know is which way the velocity is changing. You don't really know which way the velocity is, right? Newton's third law is also another law that has kind of some colloquialisms associated with it, right? And that's for every action there is an equal and opposite reaction, right? And that's the colloquialism that's associated with Newton's third law. It's not often understood very well in terms of physics because this can be a very difficult law to understand. It's very difficult to misinterpret it and to misapply it as well. When we're talking about Newton's third law of motion, you have to have two objects acting on each other. Each one of them has to be applying a force to the other one, okay? And the equal and opposite forces are always acting on different objects. They're never acting on the same object. And that's where it's most often misapplied, I think. We often come to a situation where somebody applies this to two forces acting on the same object. For example, how do I go back to the previous section? Here. In this example with the rocket sled, a lot of people would say, look, equal and opposite forces. The weight down, the normal force up. No. The weight down is the Earth's gravity pulling on the sled, pulling it towards the ground. The normal force up is the Earth pushing on the Earth's surface, pushing on the sled. Now, those are two different forces from two different sources. I didn't mean to rhyme those, but it did. But they're not acting on each other. That's the Earth's surface and the Earth's mass, the Earth's gravity. But the Earth's gravity is not acting on the Earth's surface, and the Earth's surface is not acting on the Earth's gravity. In order for them to be equal and opposite forces, the sled has to act on the Earth, and the Earth has to act on the sled. And those two forces cannot be on the same object. In this case, both of the forces are acting on the sled. So those are not equal opposite forces. That's not why they're equal. They're equal for a completely different reason, not because of Newton's third law. And that's probably the most common misunderstanding of this law, Newton's third law. A better understanding of Newton's third law, I think, comes with, well, you could go back to this sled and give an example. You could, kind of just concentrate on where the sled is touching the ground and say, okay, because gravity is pulling the sled downward towards the Earth, the feet of the sled or the wheels of the sled are actually pushing onto the track. And there's a force between the foot of the sled and the track. The sled is pushing on the track. And the normal force from the track upward on the sled is an equal and opposite force. Those two forces are equal and opposite. Sled pushing on track, track pushing on sled. You should always be able to do that with equal and opposite forces. You should always be able to make a sentence that says something pushes on something else, and then just flip that sentence around and say the something else pushes on the something. And if those two things are true, then they should be equal and opposite forces. If it's not true, it's probably been messed up somehow. But I think probably my favorite version of this is to talk about boxing. Right? They actually say this is actually done in Man of La Mancha. the great book or musical or whatever else. So Sancho, right? Anyway, Sancho is hit by his wife, right? Don Quixote asks, "Did you hit her back?" And he says, "Of course I hit her back," right? And what he meant was he didn't hit her back. She hitting him was the same as him hitting her, right? Because it's the same thing, right? She's a lot harder than me. You know what they say, whether a stone hits the pitcher or the pitcher hits the stone, it's going to be bad for the pitcher, right? That's the idea. Another way of thinking of it is whether a mosquito hits a truck or a truck hits a mosquito, the mosquito loses, right? It doesn't really matter, especially if the truck is moving very quickly. But I like it in terms of boxing, right? Why do boxers roll with the punch? You've heard that phrase before, rolling with the punches. Why is that a phrase? Boxers do this. It's one of the first things you learn in boxing, because if you don't learn this in the first day, you'll get knocked out in the first hit. Okay? You get hit in the face, you roll your head, you roll your neck, you roll your shoulders, you roll everything. You even take a step in the direction of the punch. Why do boxers roll with the punch? Yes, sir.
Kind of like disperse the tension of the shot, because like the skyscrapers won't, I know it's supposed to slow down a little, but I'm not going to be correct, it's the right leg tension. So like if they're completely still with high wind sometimes.
Okay. Yeah. I'm not sure I understood all of it, but it makes sense, I guess. I think what I'm looking for is hidden in there, because I'm looking for something less technical. You probably know more about boxing than I do, but really what it comes down to is they don't want to hit back, right? Look, go to the other extreme. Instead of rolling with the punch, lean into it. Hit back with your head. What happens? If you hit back with your head, you're gone. You might even die if somebody's hitting hard enough. Okay? In fact, it's happened in the ring before. The most famous, you ever seen the film Cinderella Man? Okay, the film Cinderella Man is about this great boxer from New Jersey who's never been knocked out. And the reason everybody says the reason he never got knocked out is because he's just a tough guy from New Jersey. No, the reason he never got knocked out is because he was fluid and loose in the ring, and he always rolled with the punches. He could take a punch and roll with it and never get knocked out. He never got knocked out in his life. Heavyweight boxer, one of the few ever to do it. I think he might have been the only one ever to never get knocked out in the ring. He's going up against a boxer from California, from my hometown, actually. We have a Max Bear Park in my hometown. It's a tiny little park. Like it's been like crushed by all these streets. But anyway, Max Bear was this boxer who was incredibly fast, way faster than any other boxer, especially for his time, and way stronger than any other boxer for his time. He was well ahead of the curve for boxing at the time. He probably could have boxed today. And that's not easy to say about many pitchers from the early 20th century. Pitchers, not pitchers, boxers. But not many boxers from the early 20th century could have held their own in today's boxing ring. But he actually killed two boxers in the ring, I think, and one died shortly after leaving the ring. Or no, and one died in his next match because anyway. The point is that Max Bear hit so fast and so hard that he actually would separate people's brains from their skull. It would separate the brain from the not from the skull necessarily, but the connective tissue would break, and that would cause the brain to rattle, and it would cause it to separate from the spine, and then that's just it. There's no fixing it. It's instant death. And one person, it didn't get disconnected, but the connective tissue was damaged, and the very next fight, the first little hit that he got killed him. He didn't do it on purpose. He wasn't a mean person like the movie portrays him. He wasn't an angry person, and he wasn't a cruel person. He was just an enthusiastic boxer, and he was doing this to make money. So he was trying to put on a show, and he was just that way. It was, and in fact, the people that he killed in the ring, he actually paid for their families' life, like paid for their living for the rest of their life, and paid for all of their kids' college education. All of these families, he paid for their life after that. He felt terrible about doing it. He really tried not to do it, but he was just that strong and that fast. But when you don't roll with that punch, if you're not ready for that punch and you don't roll with it, it can be seriously damaging, especially if you happen to be leaning into it, which is probably what happened with those three people. They were going the wrong direction, and all of a sudden, not only are they being hit, but they're hitting back. And so it's like two hits combining. It's the difference between running into a wall at 25 miles an hour and getting really injured and running into another car going 25 miles an hour in the opposite direction and dying for sure. It is so hard to survive a crash going 25 miles an hour head on. It's just, if two cars are going head on at 25 miles an hour, it's almost impossible to survive. With airbags, it makes it more possible to survive, but a very painful experience. But without airbags, you're not surviving. You're going to die. So I mean, it's just Newton's third law is all about this idea that force goes both ways. If you hit something, it hits you back. But if you don't allow it to hit you, if you roll with it, then it's not hitting you because you're not hitting it, right? Let me give you another example that's maybe a more illustrative. Anybody want to be my guinea pig? I need somebody really strong. Who's going to be my really strong guinea pig?
You want me to do it?
Apparently you look strong. He pointed at you. All right.
Alright, what we doing?
What we're going to do is get a piece of tissue paper here, and I want you to show me how strong you are by cutting it in half with a karate chop. I'm going to hold it. You're
Oh,
going to
sick.
karate chop it. Oops.
Oh,
Sorry. Go again.
it's not gonna work.
Go again. Oh,
Oh.
didn't do it. Oh, try again.
Should I count down?
Go ahead.
3, 2, 1.
Didn't do it. I mean, we thought you were strong. What's wrong with you? man?
Yeah, I don't know. I
Okay,
guess
try
not.
again. Try again. I'll make it easier for you. Right? I hit back. I held on to it and provided some counterforce. Right? But every time I didn't allow the tissue to hit back, I just let go of it and it had nothing to hit back with. Nothing happens. You know, you'd think it would be really easy to break tissue, but if tissue can't push back, you can't push it. Right? So this idea of force is a little more complex and more subtle than we think. There are so many different examples out there that really can be really weird, I guess. Have you ever been in a swimming pool and tried to get to the side of the pool by pushing off like pushing off of a floaty in the pool or something? You can't do it. The floaty just goes flying and you go nowhere. You actually have to get your hands in and push on the water. You have to push on something at least as massive as yourself, so that, you know, it goes, half of the force pushes the water back, the other half pushes you forward, but it's still hard to get to the other side of the pool. Right? Can you imagine swimming through air? You ever had a dream like that? I used to dream about swimming through the air all the time. I don't know why. Anyway, so this idea of the force counterforce is always present, even when we don't realize it's there. Whenever you push on something, it always pushes you back. Whenever you pull on something, it always pulls you back. But what's different between the two things? If the force is the same, what is different? Well, let's look at the equation. What is the equation that we have that involves force? We have these two forces. They're the same force. Here's the force. The swimmer is going to push on the wall backwards, and the wall is going to push on the swimmer forwards, or left and right, or whatever you want to call it. It's the same force, so I'm just going to call it F. But on the one side, we have the mass of the swimmer. What do we have on the other side? What is the mass of the wall compared to the mass of the swimmer? It's essentially the mass of the earth, or whatever that pool is connected to, right? It's huge. And if this mass times some acceleration has to equal this mass times some acceleration, what's going to happen to the accelerations here? This acceleration is going to either have to be super tiny, or this one's going to have to be super big, or some combination of those two, right? You're going to get a big acceleration on the swimmer and almost no acceleration on, and literally no acceleration on the earth. I mean, it's the mass of the earth is so much bigger. If this pool is connected to the earth, that there will be literally zero acceleration, even for a small acceleration of the swimmer, right? Because the mass is so much bigger. This actually happened a lot to me when I was a swimmer. I actually was a competitive swimmer for many years, and I coached swimming for many years, actually. I actually coached a guy who swam with Michael Phelps during Michael Phelps. Well, he and Michael Phelps were kind of the same age, and they grew up together in the U.S. swimming thing. My friend, the kid that I coached he was about the 6th best freestyler in the United States, which means he never went to the Olympics, because the 5 best freestylers in the United States are 5 of the best freestyle swimmers in the world. And so if you're not number 5, you're not going to the Olympics. And he was always about number 6. He never quite went to, he went to every other international competition, won lots of gold medals, but he never quite got to the Olympics. But anyway, he knew Michael Phelps. That was kind of fun. But anyway, when I was swimming competitively, we would do these kicking laps. We'd kick constantly. And it's just a common thing you do. I think coaches just do it because they don't know what to do next. And so they just give you some laps to do kicking while they think about what to do next. That's what I did when I was coaching. But anyway, you have this kickboard in front of you, and your face is above water, and you're bored out of your mind, and you're just kicking, and kicking is tiring. It's the most tiring thing to do in swimming. When you're actually racing, unless you're swimming anything below like 200 meters, you almost never kick because it just takes too much energy out of you. But I'm just kicking along forever, and we'd grab each other's hands as we were going in opposite directions, because we'd swim in kind of these long oblong ovals in the lane. We'd grab each other's hands and pull each other through the lane, right? And you'd go flying, get going faster, and it was great. My friend hated it though. My friend was the star swimmer of the team, and he was much more massive than I was. He had huge muscles and everything, big, like bodybuilder looking guy. And he hated doing that because I would go flying and he wouldn't go very far, because the same amount of force that would accelerate me a lot would only accelerate him a little, right? So anyway, he actually just a few years ago competed in the Ironman triathlon in the 40 and over age group or something like this. He went on to continue swimming, and he picked up cycling from me. Cycling is something I got him started in, but I was never a good enough runner to be a triathlete. Terrible runner, in fact. All right, so let's take a look at a different example. Here we have a professor pushing a cart of stuff, random shapes, obviously from the shape closet or something. And we're going to look at 2 different systems. First system we're going to look at is the whole system of the professor and the cart and all the stuff on the cart, right? And if we look at that system 1, then there is this free body diagram here, which shows we have a force from the floor pushing forward. That's actually pushing on the professor's foot, right? The professor pushes backwards on the floor, but the professor doesn't move backwards. The professor moves forwards. So the force that actually propels the professor forward is the Newton's 3rd law reaction force of her pushing backwards, which is pushing forwards. The floor pushes forward on the professor, right? So that is acting on our system. This is the system acting on the floor, right? The professor acting on the floor. Then there's the friction acting on the front of the cart. That's the other one in the horizontal direction. Then there's the weight of the whole system and the normal force on the whole system. That's it, right? And in the first part of this problem, they actually ask us to calculate the acceleration of the system using those forces. And they give us the force on the floor and the friction force, and then we can calculate the net force, and then we know the whole mass of everything, and we can calculate the acceleration. Pretty simple. First, you calculate the net force, then you calculate the total mass, you plug it in Newton's 2nd law, solve for the acceleration, 1.5 meters per second squared. Pretty simple. The next thing they ask for is, what is the force that the professor pushes with on the cart? What is the force right here? So we go to a new system. This system, system 2, which is the system of the cart. What are the forces pushing on the cart? Well, the professor is pushing on the cart with her hands. The friction is pushing on the cart, and then there's the weight of the cart and the normal force on the cart. Those weights and normal forces are different weights because they don't include what? They don't include the professor, right? The first system included the entire thing, the cart and the professor. The second system only includes the cart. So the mass of the professor isn't involved. Neither is the forces from the floor on the, neither is the force from the floor on the professor involved. So a different system, and we're now going to calculate the force on the cart from the professor's hand. So the net force on the cart, well, no, they want to actually know, let's see here. They want to know the net force on the cart, not the force of the professor. They actually tell us the professor on the cart. No, they don't. They do want to know that. They want to know the force the professor exerts on the cart. So that's good. Okay. That's what I thought. Okay. So they know the force professor exerts on the cart. And so they know that Newton's second law says that net force equals mass times acceleration. So acceleration equals net force over mass. And they know that the net force in system 2 is equal to the force the professor's pushing with, subtract the friction force. So there's the net force. And this is the force we're interested in, the force from the professor. So what we do is we actually are going to solve this equation for the force of the professor. And that's the net force plus the friction force. Now the net force on the system can be calculated from the previous problem's acceleration because the cart is still accelerating the same amount. So we use Newton's second law again to calculate the net force on the cart alone by taking the acceleration of the cart and the mass of the cart alone. We're not including the mass of the professor here, just the mass of the cart, because that will tell us the force that's only acting on the cart, 29 newtons. So that's the total amount of force acting on the cart, which is a lot less than the total force acting on the professor and the cart. Then we can actually solve for the force of the professor because now we know the net force and the friction added together will equal the force from the professor pushing on the cart. So it's 53 newtons. Now, in this previous problem, it was 150 newtons of the floor pushing forward on the professor because the force pushing forward on the professor had to move the professor and the cart. However, only 53 of those newtons needed to be used to propel the cart. So this is 150 newtons here, 53 newtons here, and then the friction over here. And that's how they do that. So it can be a little tricky going back and forth using Newton's, in this case, we use both Newton's second law and Newton's third laws to calculate forces. Because action and reaction laws, or action and reaction forces. What time is it? Almost 5 o'clock. Let's take a 5-minute break. Actually, it's a good time for a 5-minute break. We'll come back and crank out hopefully the rest of this chapter. What we're going to try to do with this chapter this week is we're going to try to finish all this today. And then if there are any questions on it, we'll try to answer them over email. And if we need to maybe schedule another Zoom later in the week, if anybody wants to request that, you can. We can try to do that. We'll try to do it without much, much else during the week, and then come back Monday with a minimal amount of questions, possibly maybe even no questions from chapter 4. Hopefully we'll all be done with the homework and ready to move on to chapter 5, so that we don't lose any time from that day off we had on Monday that I completely forget about every year. So anyway, we'll take 5 minutes.
science credit. I'm actually a music major, so this is completely out of my realm.
You decided to take physics as a one science class.
Yeah, well, so I go to Ivy University in Seward, Nebraska, and part of like the gen eds is you have to have like 3 natural sciences, like physics, chemistry, and biology between high school and college. So I have the other 2 in high school and just didn't fit in school year, so here we are.
That sucks.
I'm still in high school, so it's taking us to that nothing better to do.
Sick.
And I have close to 20 credits, so I might as well just get my associate's back when I graduate.
Great.
I'm gonna be a junior this next year.
Sick. Nice.
You're amazing. You're amazing. What do you want to do?
Good question. I have absolutely no idea. Probably science studies. This is my 3rd college science class. Not the first one to at college. School credits.
And educated or just sport kid?
Very bold. I would be brought to tennis ball after our it's American tennis.
I was married kids. I did that same thing, then I got really tired. Take classes over summer.
There's been some I just never make in my house. It's yeah, it's good.
What are the video game games?
All right.
So will you be pushing the homework this Sunday? Or you can do it?
What's it at right now? Yeah, we can push it to through the weekend here. Let's see. Nope, wrong class. Yeah, let's do that. And it looks like we're still on track to have an exam here in a couple weeks.
Were you on the assignment like the chapters you covered before the exam?
I usually don't do a review. But what I do is I pull the exam questions directly from your homework. So you'll have seen them before, right? Yeah, most people find that relaxing, at least, or at least a little bit of comforting because they're not like, it's not like some mysterious thing. So the best way I think to study for the exam is to just go through and look at the previous homeworks and say, what did I not understand? What did I struggle with? You know, what did I have to try several times to get done? And then just send me an email and say, hey, can you help me with this one? Or just try to figure it out on your own, watching more video or whatever you want to do to help me. That's been, I think, the biggest help for most of my students. Frankly, the way that I've designed this class, most students struggle more with the homework than the exams, just because I give so much homework. The exams are, I think, a little bit less stressful for most students than the exams are. What did I just say? The exams are a little bit less stressful than the homework is for most students in this class. I've discovered.
And you should do 2 labs this week and 2 labs next week.
You should try to, well, you don't necessarily have to do them in 2 labs this week, 2 labs next week, but you should try to do more than just one of these, lab activities. Try to get in a couple, maybe 1 week, one the next week. We essentially, by the time we get to about chapter, we want to be done with activity 6 by the time we get to about chapter 9, right about the end of June. So in June, we want to finish the rest of those 4 labs at least. Well,
Trying to do them
we,
live.
yeah, by sometime in here, sometime in probably this week or the next week, I will right about in here, I will be giving you another lab or two that are not in that series of labs. So you got a couple weeks, 3 weeks to work on those next few labs. So what is today? Today's Tuesday, the second, right? So yeah, you've got to finish, you've got probably about 3 weeks to finish those next labs up to lab 6. And then right about this week, I will give you another lab or two to work on until we're done with things. And then we'll do the rotational lab after that. And then it'll be only a couple weeks before we're done with class. Crazy. Usually gardening is my major pastime over the summertime. And I'm super excited because I'm growing popcorn this year. Colored popcorn. I'm growing, it's like multicolored gem popcorn. My wife loves popcorn. So.
Picked up roast pepper plant.
What's that?
Roast pepper plant.
Oh, yeah.
Trying to make some salsa at the end of the summer.
I love chilies of almost every kind, but this like trend of trying to find the hottest pepper in the world, I don't understand. I mean, I like habaneros. Habaneros are a nice pepper, but I'll never eat anything hotter than that. Habaneros are too hot. You can only eat them if you mix them with carrots or something else that's gonna really cancel out that terrible burning sensation. It's just not fun anymore after a while, especially if you mix them with tomatoes and onions. You're like, crap, that's even worse. So you're a stronger man than I am. If you're gonna go with ghost peppers or like Carolina Reapers, I mean, who would even eat something named that?
Me and the brother-in-law just have like a competition.
Oh yeah. I lived in New Mexico where they eat hot food constantly. The green chilies you can get in New Mexico can be so hot, and they don't even like that stuff. They're like, they call it. They have a condition that when you eat peppers that are too hot, they call it the ring of fire. They're like, you don't want the ring of fire, man. No, I don't. Those peppers just get so hot. And the funny thing is about hot peppers is that it's not actually, most people think it's some kind of acidic thing that's burning your mouth. It's not. It's just, all it is a molecule that is shaped, what's that molecule that's capsaicin, right? The capsaicin molecule is actually just shaped in just the right shape and just the right size so that it actually sits on the burning pain receptor in your nerves and it activates it. It's like a little short circuit and it activates the burning sensation in your nervous system. So your nervous system thinks you're feeling something when you're not actually feeling something. And it sends all the reactions that it should. It sends the reaction of, swelling and pumping of blood and the pain so that you won't touch it anymore. Sends all the same pain receptor reactions. So you feel it all and you get the sweats and you get all the stuff and you can get all kinds of, weird things going on, but it's not actually burning. There's no burn. It's just a pain receptor short circuit. That's all it is. And this is why some people can eat these really hot peppers and not react. Some people have learned to turn off that pain receptor. They've got that control, or they're just not sensitive to it. That pain receptor is not sensitive in their body. If you feed capsaicin to a frog, it won't feel it. Frogs don't have that pain receptor. They don't have. It's not the same size and shape, so it's a different size and shape. It's different with different animals. Birds don't mind it. Birds will eat those peppers, no problem. They'll eat the seeds out of those peppers. They love them, no problem. They don't have the same type of pain receptor. Really weird, huh? But most animals don't eat hot food, so they don't need those pain receptors in their body. Most animals eat cold food. We are the only animals that cook our food. So we have to have those pain receptors inside of our mouths. We're dumb that way. If we were birds and didn't cook our food, we wouldn't have this problem. Yeah, it is kind of cool. It's weird, but it's I don't know. Food science is one of my favorite sciences. I really am considering starting a class on food science next semester. So the physics of food. All right. Normal force, we've already talked about it. You know, put a bag of bow wow chow or some kind of chow on a table, and the thing that keeps it from falling through the table is the normal force, right? So we often use capital N for normal force. We also use it for the Newton. Sorry about that. We just ran out of letters in physics. So. But here's a problem where we talk about a normal force that is not necessarily perpendicular anymore. The skier. In this particular problem, we're going to actually rotate our axes. So instead of having a horizontal vertical axis, we're going to rotate our axes so that they're in line with the plane of the hill, with the slope of the hill. Why would we do that? Well, because it actually makes less work for us. We have in this free body diagram that we draw here, we have a normal force that's pointing perpendicular to the slope. We have a friction that is pointing parallel to the slope, and we have a weight that's pointing at some angle to the slope. And since these two are already pointing perpendicular and parallel to the slope, why don't we just put our axes in those directions? Then we don't have to calculate we don't have to do any calculating of the components of those vectors, right? Those vectors are pointing already in the directions of our coordinate system. So it just makes less work. So we call this the perpendicular direction and this the parallel direction, just convenient for convenience sake. We could call it X and Y if we wanted to. We just use that for convenience sake so we know that we've rotated them. And then the friction is pointing all in the parallel direction. It has no perpendicular component. The normal force is pointing all in the perpendicular direction. It has no parallel component. And the only thing that's going to have components is the weight force, which pulls straight down towards the center of the earth. And it's going to have a perpendicular component here and a parallel component here. And this is where the trigonometry gets a little bit weird, because now we're looking at this angle here to be 25 degrees, and this one here is 25 degrees. A little trick that I use when I'm drawing pictures like this, as I try to draw, whenever I have an inclined plane kind of problem, I draw it in its extreme. Instead of, let's say that the angle is 30 degrees or something. Instead of drawing a 30-degree angle, I draw like a 5-degree angle or a 10-degree angle. It doesn't matter in the drawing. Nobody's going to measure it, right? But I make it extreme, and the reason that I make it extreme is because when I draw this weight vector from the slope that comes straight down like this, and then I draw the perpendicular component of it, which is going to come down like this, you can see that this is definitely the smaller angle. Whereas if I draw it more, like it would be for a 30-degree angle closer to this, then you draw this thing here, you're like, well, which angle is which? I can't remember which one. Is it this one or is it this one? I just like, it just makes sense. You can also prove through geometry that this angle is 25 degrees if this angle is 25 degrees, but it's a pain in the neck. These two triangles are going to be similar triangles if you remember anything about geometry. That's going to happen, but you're just not sure which one. You just make them extreme and then you'll be sure. It's just that easy. So anyway, what the weird thing that happens here with the trigonometry though is that this parallel component, which we might consider to be more horizontal, is now opposite to 25 degrees. So this component down here is actually going to be our sine thing. This W parallel, since it's opposite the 25-degree angle, is actually equal to the weight times the sine of 25. And this one, which seems like it's more perpendicular or more, which seems like it's more like up and down, more like the Y one, anyway, is going to actually be next to that angle. So that's going to be W times the cosine of 25, which seems a little bit different than we've been doing before. Of course, you can always just choose this angle, and that, since this one's 25, this one up here has to be 65. Then you could use this angle, and you could still use sine here and cosine here. It doesn't matter one way or the other. It's up to you. But that's the only really weird thing going on here. And once we know that, then we can just split it into two things. We'll do the math in the X or the perpendicular direction, math in parallel direction completely separately. They start off with the parallel direction, the acceleration in the parallel direction is equal to the force, the net force in the parallel direction divided by the mass, Newton's second law. And the net force in the parallel direction is just the part of the weight that's pulling the skier down the slope. It's just this thing right here. If there's no friction. In part A, there's no friction. So the only force in the parallel direction in part A, since there's no friction, is going to be the weight, the component of the weight that's in the parallel direction. That's what pulls them down the slope. That's mg sine 25, and then you divide by m, and that ends up just being g sine 25. So it doesn't matter what the mass of the skier is. It only matters what the slope is. That's the only thing that affects the speed of the skier at the bottom, if there's no friction, right? If there is friction, then friction is affected by the weight of the skier. We'll learn about why it's affected by the weight of the skier in a bit. But in part B, they do it with the friction. So they tell us how much friction there is. So you have to take the weight of the skier in the parallel direction, which is this force here, the part of the weight that points down parallel, subtract off the friction, and then divide by the mass, and then that will give you the acceleration. So the acceleration without friction, 4.14 meters per second parallel to going down the slope. With friction, 3.39. It's less, it should be, right? And so when you need to resolve the weight into components on a slope like that, you just got to be a little bit careful knowing which angle is which and knowing which component is which. And remember that the parallel and perpendiculars should add up. I don't like the way they draw them here where they put the parallel one up here. I like the way they draw it in the problem where they put the parallel component down here to show that this weight perpendicular adds up to the weight, adds up with the weight parallel component, this being the weight parallel component. It actually adds up, putting them, head to tail to equal the weight. Because sometimes what people do, and that these two should be perpendicular to each other always. But sometimes the mistake people do is they'll say, oh, I need to go down to here and then over to here. And they use those as the components. Well, those aren't the components of this vector because they're not 90 degrees to each other here. The components of a vector should always be 90 degrees to each other. So you got to make sure that your components are 90 degrees to each other. One of them perpendicular, one of them parallel. So I like drawing these. Yeah. Tension is another kind of thing that we run into when you have forces that transmit themselves through some material. It happens a lot, actually. There's an entire year devoted to this in engineering. That for a very simple example would be you're holding a rope and you're pulling up on the rope, and the force actually transmits itself through a tightness, you could think, in the rope, which we call tension. And that tightness pulls up on whatever's connected to the end of the rope, in this case, this mass block thing, right? And gravity, of course, is pulling down on the mass, and the rope is pulling up on the mass, and you're pulling up on the rope, and the rope is pulling down on you. But the tension, the interesting thing about tension is that it transmits itself through the rope so that it's equal on both sides of the rope, as long as there's nothing intervening in between. And it can actually turn corners, or if it's a rope or a chain or a cable, you can turn it, and that tension will turn as well. It will actually turn the corner with the rope. Now it can get fairly complicated when you do stuff like that. We're gonna leave out the complications for the most part, because they're negligible for our purposes. But this whole tension thing brings up all kinds of interesting situations. Of course, there are all kinds of tensions in your muscle. This is the reason that tendons are called tendons, is because there is tension in them, right? So one of the most prominent tendons in your body is the one in the crook of your elbow, which connects your bicep to your forearm. It connects your bicep to your forearm just a couple of inches from your elbow, and your forearm weighs, for an average person, somewhere between 10 and 20 pounds, 10 and 15 pounds. It's fairly hefty appendage, right? Just to hold up the weight of your elbow or the weight of your forearm, feel the tension in your tendon. Just put your arm at a 90-degree angle like this, holding up your arm, and feel the tension in that tendon right there. It's almost 100 pounds of tension just to hold this thing up. Well, it's more like 50 pounds, but it's a lot. Put a book in it, feel it increase. It's a lot more. You can really feel the difference just with 5 or 10 pounds in your arm, on the end of your arm. It's a huge amount of difference. You know what happens if that breaks? You don't want to know. There's so much tension and so much muscle pulling on that. If that breaks, the whole thing shoots up into the top of your arm into a big ball of muscle and tendon. It just, because that's the only thing holding it in there. That's the only thing holding your muscle to that bone. And all that force in there will just right up in there. It happens sometimes, particularly to athletes, weightlifters are particularly susceptible to this. They push their tendons to the extreme and then they rip a tendon, break a tendon, and shoots up in there. Happens to other players, jumping players that jump a lot, basketball, track, volleyball. They'll break a tendon down somewhere in their leg or foot and shoots up into their leg. You gotta dig it out and reconnect it. Never really is the same again. Not very fun. Bad. Here's a bicycle. So a bicycle is designed with these triangles. You have what's called the rear triangle and the front triangle. And the reason that they're designed with triangles is because the forces involved on the bike actually cause the bike to twist down this way. Like if you push on this seat here, so it's actually not tension here. It's usually compression here. So this top tube and this so this is called the top tube. This is called the rear. This can't remember what this one's called. This one's called the seat stay. That's what it's called. I used to be a huge into cycling, so I'm trying to remember these terms. So this is the top tube. This is the seat stay. Usually these are in compression, where the forces are actually tightening them up, pushing them together. So they're in compression. These ones are actually being stretched because you're sitting down here, and these ones, this bottom one is called the chain stay, and this one's called the down tube. They actually get stretched, and the other top ones get compressed. And metal is much stronger if you're trying to compress it or stretch it than it is if you're just trying to bend it. So if you just had one tube going from here to here, and you were just sitting on top of the tube, you would be bending in the middle, and it would bend really easily. It'd be really easy to bend one of these tubes. On the most expensive bikes in the world, my favorite being probably my favorite bike company being Specialized. It's an American bike company. It's one of the best in the world, actually, even though we're not really big into cycling in this country. But this bike company is my favorite bike company. A bike like this, which is their top end road bike, the walls of their tubes are like a millimeter thick. They're super tiny walls, but they don't have to be very big because all you're doing is stretching them on the top, compressing them on the top and stretching them on the bottom. Stretching a tube with thin walls is hard to stretch. Bending it in the middle is not hard. You can really bend, but they don't put any weight there. They don't put any, and they're not made of metal either. They're made of carbon fiber. So it's actually hard to bend it in the middle. You can break it in the middle with a hammer, but they don't do that. So, so these bikes have super thin walls. They only weigh about this whole bike probably weighs about 17 pounds. It's super lightweight. And it's made completely out of carbon fiber. The only things that aren't made of carbon fiber usually are the discs in the brakes and a couple of parts that are, I'm not sure if there are any other parts actually. Everything else is made of either carbon fiber or some kind of ceramic. They're made of super light materials. But the whole idea behind this is that you transfer those forces through the material depending on the direction the materials are pointing. Instead of having it bend in one direction, you stretch it in another direction. It's the same with I-beams. You've seen I-beams on a building before, right? So if you have, let's see, I actually have an I-beam here somewhere. They used to have a rubber I-beam. We had a rubber. And if you turn the I-beam one way, it makes it really easy to bend it. You turn it the other way, even though it's made of rubber, it's really difficult to bend. Used to be on the shelf over there. So even an I-beam made of rubber has this kind of thing going for it. And the reason it works with I-beams is because in an I-beam, the cross section of an I-beam, if you cut it, down the middle of it, looks kind of like this. Kind of looks like it's got a flange on the top, and then it's got this connector in the middle and a flange on the bottom, like that, right? That's what the I-beam looks like. Well, the I-beam is designed to be placed like this. You put a concrete wall underneath it like this, and then you put a slab of concrete on top for the next floor or whatever. The I-beam is designed to use this way. And if you turn it sideways, it kind of looks like this, where you've got the top and the bottom flanges and the middle piece in the middle. And so you can put a big floor all the way across this thing. And you can support it on each end and not have to support the middle. And this thing will hold all kinds of stuff up here. You can put a car up here or whatever else. And what's going on here is as you push down here, it actually is causing tension in the bottom flange, in this part right here. So it's like trying to stretch this big plate down here. And it's also causing compression in the top. In the middle, it's just connected the two. And that's important because they need to be connected. Otherwise, it's just a flat piece of metal. But if they're connected like this, then the top compressing and the bottom stretching are kind of related to each other. And they don't want to do that. It doesn't want to compress on the top. It doesn't want to stretch on the bottom. And so it stays very, very rigid. And that's the beauty of I-beams. You could do the same thing with a big block of steel like this, but it would weigh 10 times as much. And so its own weight would bend it. So you just cut out the parts you don't need. The only thing you need is the top and the bottom, the parts you're going to stretch and the part you're going to compress. The stuff in the middle is not doing anything. It's just there. So you just remove it, right? Anyway. So tension and compression are types of forces that we often work with in physics and engineering and other things. And here's an interesting situation. We have the tension in a tightrope. Here we're gonna stretch a rope and we're gonna push down on it with this person standing on it. The weight is down. However, what is holding up? What's the force holding up the tightrope walker? Well, it's the tension in the rope. The rope bends a little bit, not much, but a little bit. And so the tension in the rope is actually pointing sideways mostly, but also upward a little bit. There's a little bit of tension pointing upward on each side. So this is the free body diagram. You have the weight and then these sideways, slightly upward pointing tensions. And if you break these into their components, you can see that you get a tiny itty bitty component on each side. These two components have to add up to be the weight of the tightrope walker. So if the tightrope walker is 200 pounds, this one has to be 100 pounds, and this one has to be 100 pounds. And if this one's 100 pounds, how long is this one? Well, if this one's 100 pounds long, right, because it's a vector, then how long is this one? About 10 times longer. So it's about 1,000 pounds of tension, right? So the tension that's actually in the rope is 1,000 pounds of tension to give you just this tiny little component of 100 pounds that's going to hold up the tightrope walker. So how strong does this rope have to be for a tightrope walker? Pretty strong, right? It has to have 1,000 pounds of tension going each direction. So it has to be able to handle over 2,000 pounds of force to hold up a 200-pound person. So you get a lighter tightrope walker. It doesn't really matter that much. You get a half as big tightrope walker. it's still 1,000 pounds in each direction. You know, it's not going to be easy, or still 500 pounds in each direction. It's still going to be significant. You're going to have a very strong rope. It actually will do better the more it bends. If it bends more, it'll actually hold more. So you've ever heard of the sport slacklining? There's a sport called slacklining. It's done very commonly by mountain climbers, where they put a line, usually a ribbon, between 2 points. Usually they put it between 2 mountains, and then they walk across it. They balance across it, but it's not nearly as tight as this. It stretches much more, so it doesn't have to be as strong. So, and then they walk across it like crazy people without any protection. If they fall, they just grab the rope and swing, with 1,000 feet of open air underneath them. They're totally crazy people. What's that? Yeah, one of the best slackliners ever to live died recently. He didn't die from slacklining, which was not surprising, because he did all kinds of other crazy things. He also was a free soloist, so he climbed mountains without any protection all the time, and he was very, very loose and crazy about that. Very good at it. But the other thing that he did a lot of, which is what he died in, was base jumping. So he base jumped off of El Capitan in Yosemite, and he was trying. They were trying to go through a canyon, so they were flying through a canyon with wingsuits, and they went in one side and didn't come out the other side. And the really tragic thing about that is his fiance, who he had just proposed to like the night before, was watching him when he jumped. So it was a terrible thing for everybody who survived as well, unfortunately. But she didn't actually watch him hit anything. She just watched him enter the canyon and watched him never come out. So very sad for her. Rock climbing and mountain climbing is another thing I used to do a lot. I used to do a lot of crazy things before I became a dad and had responsibilities. Anyway, okay, so they do the math here. You can see that we have a very small angle because it is a tightrope, so it's not going to bend much, 5 degrees. And so we can calculate this out here. In the Y direction, we have these 2 tensions that are going to equal, that when we add them together, they have to equal the weight of the tightrope walker if these are going to cancel out. Because we want them to equal. If they don't equal, of course, the tightrope walker is going to fall because the forces won't cancel to be 0. So when we solve them to be equal, we end up with this equation here. So that this is the tension on the left side times the cosine of 5 degrees equals the tension from the right side equals cosine 5 degrees. And once we solve all of these equations, we will actually be able to calculate that tension. So in the Y direction, we get tension from the left Y plus tension the right Y minus the weight has to equal 0. We know that the tension from the left has to equal the tension from the right, so these 2 T's can be equal. The 2 T's after we put the sign of the angle in can be equal. And the net force in the Y direction ends up looking like this. The tension in the rope times the sine of 5 degrees plus the tension in the ropes times the sine of 5 degrees again, minus the weight equals 0. So the weight has to equal 2 times the tension times the sine of 5 degrees. And we solve for tension and we get 2 times mass times gravity, which is the weight over 2 times sine of 5 degrees. So the tension has to be 3,900 newtons, which is very significant. So what's the good news? The good news is you can use this to your advantage. So you've ever seen somebody stuck in the snow in their car, right? And people pushing on it, they put a cable on it and they try to pull it out. The best thing to do is to come along as a know-it-all physics student and to look around for something that can't be pulled, like a tree or something big, and then tie the car to that thing and then just push sideways on the rope. Because you know that if you put a small force sideways on a rope that's in great tension, it will create a huge amount of tension in the rope and be able to pull that car out. You can apply essentially 1/10 the amount of force and get 10 times as much force out just by pushing sideways. And that's what they're doing here. Beautiful, isn't it? I've used this to my advantage many more times than once. It's also used in things like bridges. It's my favorite bridge because it's the one I grew up with. Has anybody been to the Golden Gate Bridge before? You get to walk across it. I love walking across this bridge. When I was a kid, you could walk across it and there were no nets underneath. Like they put all these you see the nets and the grills that they put on it now, protect people from falling. They had a kid fall in between once. Didn't actually fall to the water, just fell and got stuck in there. But they've had plenty of suicide people jump off there. But anyway, before they had all those nets, you would be walking along the sidewalk and you'd look down and right next to you would just be this gap going all the way to the ocean. And it's like 250 feet at one point, I think. But anyway, what these cables do here that are connected to the roadway is they transfer weight into tension into the big cables here, the suspension cables, right? So the suspension cables are connected to these huge blocks. They go all the way down here, right down here, right to the south of Fort Point. That's what this is, an old Civil War era fort. There's these huge blocks of concrete, like the size of apartment buildings, and the cables just connect right into those blocks of concrete. And they have the same ones on the Salinas side over here on the North Peninsula. And the ones on the North Peninsula, you used to be able to go along the beach and walk right up to it. And they probably have them all fenced off with guards now, all the security stuff we do these days. But you used to be able to walk right up to them and like touch them on the beach. But anyway, that is what's going on there. You're transferring downward force. You're pulling down on the cable and it creates a tension this way, just like pushing this way creates a tension this way. So in the problem solving strategies section, here they talk about, the steps to solving one of these problems. Step one, what is it? Define a system of interest. I mean, they say that you should actually circle it. That's fine if you want to. I think the most important thing is to recognize what forces are acting on your system of interest and which ones are not. And then labeling those forces, making a free body diagram. And then, of course, you want to know what you're trying to figure out, identify the things you're trying to calculate, for example. You may want to write down some equations that might be necessary. You might need to calculate some things. You might need to use some kinematic stuff to calculate something that you need. Maybe you need the acceleration and you can get that from information they've given you, for example. But once you've figured out what needs to be calculated and things that you know so that you can calculate it, then you want to apply Newton's second law in 2 dimensions if necessary. So you might have to apply it once in the x direction, once in the y direction. Force equals mass times acceleration. Of course, if it's not accelerating, then it's just the sum of the forces equals 0, right? If it's like Tarzan here, Tarzan's just hanging there. He's not accelerating. So the upward forces and downward forces add together to equal 0, and that's enough to solve sometimes. That's you don't necessarily have to have an acceleration to solve Newton's law, because it just makes it equal to 0, and then you solve for one of the forces in terms of the other forces. That's totally fine. But if there is an acceleration, you need to include that. Here they do a bunch of examples of this. So here we're going to do a drag force on a bar. So a drag force is like friction, but in a fluid. If you're in a liquid or a gas, friction is called drag because it acts on more than one point or more than one surface. It acts in more dimensions, in other words. But we have these 2 tugboats, one pushing this direction with this force, one pushing this direction with this force. And they tell us that the acceleration, let's see, direction. They tell us the acceleration is 7.5 times 10 to the minus 2 meters per second squared, and they tell us it's in this direction, okay? That means that we know the direction of the force, because the force and the acceleration, the net force, not any particular force, but all of the forces combined have to add together to equal a vector that's pointing in the exact same direction as the acceleration. So now we know the exact direction of the force because they told us the exact direction of the acceleration. But we're missing one of our forces. There is a drag force. Drag forces always act in the exact opposite direction as the movement of the object. So we're going to assume, let's see. Yeah, so it says right here, the drag force opposes the motion of the object. So it goes in the exact opposite direction as the object. So we're going to assume that this thing is also moving in this direction, even though they don't say that explicitly. We're going to assume that the velocity is also in this direction. So it's starting off with 0 velocity and then being accelerated in this direction. So its final velocity will end up in that direction as well. So the reason we have to assume that is because then that tells us what direction the drag force actually is. It is actually also in that at that angle. So here is our free body diagram. We have force Y, force X, force drag, where the drag force is at that 53-degree angle with respect to the horizontal below it here. And if we wanted to add all of the forces together, to calculate the net force, then we would have a net force that is going to be pushing this direction, which would be the sum of the applied force, this one here, and the drag force, which takes a little bit away from it. So this force, which is the applied force, which is the sum of these two forces, the applied force minus the drag force gives us this net force here. So that's what this drawing is about, where F of X and F of Y are these two forces from the two barges. So that's what those diagrams are all about. In the end, we can split it into the X and Y directions just fine, or we can deal with it along this 53-degree angle, because if we break it down into this 53-degree angle, then it's all in one dimension. So what we'll do is we'll add the force X and the force Y together to get us our total applied force. And that's what they're doing here. Applied force is equal to force X plus force Y. That's of course a vector calculation. And so it's essentially it's essentially going to be the hypotenuse of that triangle. So we use the Pythagorean theorem to calculate the applied force magnitude to be 4.5 times 10 to the 5th newtons. We already know the angle is 53 degrees. They calculate it anyway. They find out that it is 53 degrees, and that's fine. But then we apply that other equation. We know that the net force is equal to the applied force minus the drag force. And then we're going to solve for the drag force. The drag force, I like doing it my way better. Solve for the drag force. The drag force would then be equal to if I add the drag force to both sides and subtract the net force from both sides, then I would get the drag force equals the applied force minus the net force, right? But we also know the net force is equal to mass times acceleration. So we replace net force with mass times acceleration, and we get drag force equals applied force minus mass times acceleration. And we know the applied force. We just calculated that. We also know the mass and the acceleration. We've been given that. So we just calculate the drag force from there. Pretty straightforward. Here's one that gives a lot of students issues. There's a homework problem almost exactly like this. So remember to reference this problem. Where you have a light hanging from 2 posts, 2 cables, 2 different angles, right? This cable over here is pulling more to the side, so it's going to do less lifting. This one's pulling more upward, so it's going to do more lifting. That's kind of a way to think of it. This one's doing less lifting because it's pulling more sideways. This one's doing more lifting because it's pulling more upwards. Just a thing to think about. We have to label these forces. They go ahead and label them on the diagram. They label tension forces and they label weight of the light. But our system of interest is just the light. So our free body diagram is just this point representing the light, the tension from cable 2, the tension from cable 1, and the weight down. That's it. 3 forces. The tension cables are going to have components, horizontal and vertical components. And the vertical components are the things that are going to have to hold the light up. Right? So this one plus this one minus this one has to equal 0 because the light's not going anywhere in that direction. That's Newton's law. That's Newton's law. They actually rewrite their diagram. I like the way they rewrite this force diagram, this free body diagram with the components just kind of lining them up and showing how they should cancel. Because it's not going to move side to side either. So these ones have to cancel out and these ones have to cancel out in this. This is a completely static situation, nothing moving. So all the accelerations are 0, so all the forces have to add to 0 in every direction. In the x direction, tension 2x minus tension 1x has to equal 0. This one minus this one has to equal 0 for it not to go side to side. So that means tension 1x has to equal tension 2x. That means tension 1 times cosine 30, that's this component right here, right? Has to equal tension 2 times cosine 45, which is the right side component. And you can solve that for tension 2 and confirm you can solve for tension 2 in terms of tension 1. This isn't an answer. This is kind of a clue. If you can find tension 1, then multiply by 1.225 and you'll get tension 2, right? But it's halfway there. From the y direction, we learned that tension 1 in the y direction plus tension 2 in the y direction minus the weight has to equal 0. This one plus this one minus this one has to equal 0, right? We happen to know what the weight is, and we have these calculations for the tension 1y and tension 2y. So we can go ahead and now use this equation for tension 2. Plug this in for tension 2 into this equation right here. And then this equation has nothing but tension 1's in it. And we can solve it for tension 1. And we do. Turns out tension 1 is 108 newtons. And we already know what to do with tension 1. If we have it, we plug it in here, calculate tension 2. And then we're done. So in this particular case, we're solving for 2 unknowns using 2 different equations, which of course you can do. If you have 2 equations that are independent and orthogonal, then you can solve. Oh, this one also gives people headaches, because this one is the how much do you weigh in an elevator problem, right? So this one we have a moving frame of reference. Our system of interest is actually moving. Not only are they moving, but they're changing their movement. They're going to accelerate at some point, right? And so we have multiple forces involved. You define your system of interest many different ways. It can get really confusing. In this particular problem, they tell us the mass of the person, and they want us to calculate the scale reading as the elevator accelerates upward with an acceleration. So we know the acceleration of the elevator of the system, or if it moves upward at a constant speed of 1 meter per second. So we know the acceleration for part A, we know the constant speed for part B. So this is our diagram to start with. We have a tension in the cable above the elevator. That's pulling up on the elevator. We have the weight of the person in the elevator. That's just a constant amount of force that the earth pulls on this person with. We have the force of the scale pushing upward on the person. We have the normal force acting on the scale from the floor of the elevator is pushing on the scale with this normal force. We have the force of the weight of the scale. Gravity's pulling on the scale. Gravity's pulling on the elevator. They put this little dash in there to show that this is a much longer arrow than it actually is here. They do the same thing up here for the tension. These are really big forces here and here. We also have the force of the force of the, it's force P. I always forget how they label these. So yeah, force P is the person pushing down on the scale. And why is that not the same as the weight? Well, because we know it's not the same as the weight. The scale changes. It feels a different force as you're moving through, as you're moving in the elevator. So that's the thing that's changing here, right? We also have the force T, which is force T. What do they call force T? The force of the scale on the floor of the elevator. So that's the scale pushing on the elevator. So the force T includes the force of the person and the weight of the scale. In other words, so that's how much force the scale put. So they put a lot of stuff in this diagram. If our system of interest is the person, right? then the only forces actually acting on the person are the weight from gravity pulling on the person and the scale pushing up on the person. And that's actually our system of interest, because we want to know this thing right here. We want to know this force that the scale is pushing on the person with, because that's what we feel. That's what we feel when we feel our weight, is the earth pushing on us. So that's the thing we're looking for, F sub S. So if that's the case, then Newton's law says the net force equals mass times acceleration. Okay. Well, we don't really, the net force has two forces involved. It has the force of the scale pushing on the person, which we don't really know. We know the weight of the person, that's easy. That's just the mass times gravity. So we get this thing equal mass times acceleration now. The Fs minus W is equal to mass times acceleration. Well, we're trying to find Fs, so we solve for it. We just add weight to both sides and we get mass times acceleration plus the weight. Well, this is mass times acceleration of what? Well, acceleration of the whole system, which happens to be the acceleration of the elevator, right? So we are actually done. If we know the acceleration of the elevator and the weight of the person and the mass of the person, which is our system, we can calculate this. We're done, right? We plug in the numbers. Part A, boom, done. Boom. 825 newtons, right? If they scale, and it does matter. The sign of the acceleration matters. So this G should be a negative number, right? Well, actually, here they wrote it as a negative already. Here they put it in as a negative weight. So G needs to be positive because they put it in that way. But this number here matters. If the elevator is accelerating upward, then it needs to be a positive A. If it's accelerating downward, it needs to be a negative A, because that will make a difference here. If it's accelerating upward, we actually feel more weight, right? This would be a positive number. Both of these would be positive. It's going to give us more force on the scale and more weight. If it's going down, this is going to be a negative number. It's going to take away from our weight, and our weight will be less and we'll feel less, which is exactly what we feel, right? So the signs matter in the A. In the G, we already chose the weight to be negative by forcing the negative sign here. So we have to put G as a positive number. And that's like I said, I think confusing the way this book treats gravity. I would never, I wouldn't do it the way they do it, because this makes sense if you do it the way I do it. If you do it the way they do it, it can be confusing. Anyway, point being is that it works. And if the scale is stationary or moving in a constant velocity, so the acceleration is 0, then this is what you get, 735 newtons. It doesn't matter if the elevator is moving or if it's moving in a constant velocity, it gives you the same answer both ways, because acceleration equals 0 for both those situations. And you get just the weight of the person on the scale. Here they do another one. This one they're doing, they're combining kinematics with Newton's laws. So you have to do some kinematics first and then solve. You use kinematics to solve for the acceleration, then use acceleration to solve for the force. Not that difficult. And that takes us to the last section. Last section is about the 4 fundamental forces of the universe. We've already talked about this a little bit. But it has been discovered and determined that there are only 4 forces in the universe. That all other forces are related to, caused by these forces. The forces that we're most familiar with in our experience is gravitational force and electromagnetic. And of the two, the electromagnetic is more prominent in our lifestyle, in our lives. Everything that we touch, when we touch it and we feel it, we push it, we pull it, we grab it, we move it, we lift it, we do whatever we do, all that is electromagnetic force stuff. All of it. The muscles that cause those movements, that create those movements, are all electromagnetic stuff. Everything in chemistry and biology is electromagnetic. All of it. No, there's absolutely no caveat there. It's all electromagnetic. Pretty much everything to do with life on this earth is electromagnetic. Okay. The only thing that's gravitational is the thing that's holding the earth together and holding us on the earth. That's pretty much, and you know, any action going up and down in the gravitational field of the Earth, that's gravitational. But everything else, electromagnetic. Even when you consider planes flying through the air, that's an electromagnetic thing. That's actually an interaction between the fluid that is the air and the wings that are on the airplane. And that's electromagnetic. Those are masses pushing on other masses. Flying is electromagnetic. So gravitational is only responsible for causing things to fall, essentially, in the magnetic field, or to move closer together in the gravitational field, rather, to move closer together in the gravitational field, and to hold the Earth itself together, and to hold the atmosphere around the Earth, and to hold the things in orbit around the Earth and stuff like that. That's all it's responsible for. Everything else is electromagnetic. Now, weak nuclear and strong nuclear are also a very big, important part of our lives, but not something we notice, not something we have any intuition for. The strong nuclear force is what is responsible for holding protons together, to hold not only to hold the protons together themselves, to keep the protons, because protons are made of smaller particles called quarks, and quarks are held together by the strong nuclear force. But also inside the nucleus of an atom, you have a whole bunch of protons next to each other, and they don't like to be next to each other, especially that close. They are so close together. The protons in the nucleus are 1,000 times closer together than the size of the atom. So the nucleus of an atom is 1,000 times smaller than an atom, essentially. Okay. If an atom was a baseball stadium would be the atom, essentially. That's kind of the difference there. Okay. So it's not a lot of space. Protons do not like to be close together, but the strong nuclear force is so incredibly strong that it will force them to be together. It can hold them that close. What is the difference? If the electromagnetic force was equal to 1 Newton, right? Then the strong nuclear force would be 100 times greater than that, at least. Okay. The gravitational force is so tiny compared to that. It's 10 to the 38 times smaller than the strong nuclear force. It's so weak. It feels strong to us because the mass of the Earth is so huge. But the gravitational force between you and I in this classroom, there is gravitational force between us. It's pulling us closer together, but not enough to really overcome anything. Even the friction in the air between us is way bigger than the gravitational force between us. So we're never going to be pulled together by gravity, really. It can happen. It has happened between, hang two big tungsten balls in a room on some kind of an apparatus that allows them to move closer together without, with hardly any friction, seal up the room and leave them there for like months and months. They will get closer together by gravity, marginally. It'll take a long time, but it does happen. And tungsten being this hugely dense metal has a lot of mass. So the more mass you have, the more gravitational force you have. But it's extremely weak. Strong nuclear force, extremely strong. And then you have this thing called the weak nuclear force, and that happens. The weak nuclear force is the force that causes interactions within the nucleus as these protons are interacting with each other and kind of pushing each other around in the nucleus. Bad analogy, I guess, because we really don't know what they're doing in the nucleus. We have really knowing. But as they're interacting in the nucleus, there is some kind of force going on in there that causes release of energy. We call it radiation, right? And that release of energy that comes from the nucleus can be in the form of pure energy, like light, X-rays, gamma rays, things like this can make the Incredible Hulk, or it can actually be in the creation of a particle that can actually create an electron out of pure energy. It can create a proton out of a neutron. That actually is the same result, the same thing. The same reaction that creates an electron creates actually a proton out of a neutron. A neutron decays into a proton and an electron. But anyway, the point being is that the force that causes these strange reactions to go on inside the nucleus that are very mysterious and very few people know much about them. Mostly it's physicists and a few chemists that know something about these things. That's what that force is. And it's probably, to me, it's the most mysterious as far as just knowing things about it. But overall, I think the overall most mysterious force of these forces, even though all of them have their own weird, quirky mysteries, is the gravitational force. Because of all of these forces have an attractive and repulsive nature. They can either attract or repel. Gravity only attracts as far as we can tell, right? Matter attracts matter, and it doesn't even matter if it's antimatter, because there is such a thing as antimatter. We've actually observed it and created it, but it doesn't seem to matter, no pun intended. It only has this attractive quality. And each one of these forces also has a particle associated with it. The particle is always exchanged when the force is applied. So for example, if two electrons are repelling each other, there's actually a particle that's passed between them. It's, in the case of electrons, it's a particle of light. It's a particle of light energy that is passed between them that causes them to repel. It's part of the interaction. We assume that that's true with gravity, but we've never been able to detect the particle. We're close. We actually detected waves of gravity, which is a big step towards actually detecting particles of gravity, the carrier particle of gravity. We know what it should be. We know it should have no mass. From the theory of it all, we know, at least if the theory is correct, we know that the particle should have no mass. We know that it should travel the speed of light. That's evident from how gravity behaves in the universe, that it should travel the speed of light. Not all particles do. But the graviton has yet to be discovered. When it does, I think it will open a huge chapter in science and technology. You watch these science fiction shows where spaceships are able to travel long distances without, completely destroying the people in the spaceship, which would be the case if you traveled those speeds. The acceleration that would be required to get to that speed in, a person's lifetime would flatten the person against the back of the spaceship like a mosquito on the truck kind of thing. The ability to do that is probably tied to understanding gravitons, to understanding gravity, because gravity and acceleration are the same thing according to Uncle Einstein. So there's your education on the four fundamental particles and the four fundamental forces of the universe. We've never been able to find another force that isn't tied to these four forces, that isn't one of these four forces. It's never been done. This is not an old theory. This is a pretty new theory. It's less than 100 years old. So that's pretty amazing, I think. Have a great week, and we will see you on Monday unless anybody requests audience before then. May the force be with you, or the four forces be with you.